Our first example will be a quality of life index, or QOL, using Euclidean distance. The data for this is from the Lecture 6 data folder. The quality of life can be affected by distance and how far you are from certain amenities. Certainly you can think of this for yourself. Where would you like to live? You'd probably like to live in a place that has great neighbors. That's one thing. Perhaps in a region in which you have friends living, or a region that you just simply like. So you find a particular region in which you like, let's say you like Ottawa or downtown Ottawa. Then you start to think about other things that could be important to you. Do you plan on having a family? If so, the distance to schools might be very important. What about medical care? Certainly that's important to be close to. Fire halls or fire suppressions, these can be important to be close to. And at the same time, it can be equally important to be far away from some things, such as airports, major airports, as they can be quite loud and cause a lot of noise pollution. So there can be many things which are important to the quality of life. Finding the best place to live obviously is a multi-criteria decision-making issue. And so we need to identify certain factors that are important, let's say in general. And we can see these factors as a function of distance for many criteria. It's better, as I said, to be far from airports, even hydro lines, just to prevent electrical interference with your own electronic devices. And there may be health concerns as well related to hydro lines. Whereas it's better to be close to schools, fire and police stations, just for physical safety, recreational trails and water for healthy living as well as mental healthy living with the natural, inviting environments around you. It's also good to be close to major transportation routes, like major roads, but not too close. Think, for example, of the 417. If you're too close, you'll have a lot of noise pollution, as well as air pollution. So it's better to be a bit further away than very close to those, but not too far away that it becomes inconvenient for you to live and undertake your daily activities. Here is a cartographic model of such a quality of life index. We have schools, police stations, fire stations, and a number of other criteria, such as paths and trails, airports, hydro lines, and major routes. So we can create a Euclidean distance surface from each of these. Here, for example, we create a Euclidean distance surface from schools, and that outputs a distance surface, which we can keep as distance. Because remember, when we look at the multi-criterion decision-making or multi-criteria evaluation, one step is standardization of variables. And it might be that distance itself can be used as a standardized variable. So if we're computing distance for each and every one of these different criteria or factors, well, we might be able to keep it at that level and simply work with distance. However, how far you are or how close you are to certain amenities might be different. For example, we could consider being within 500 meters of a school very good, and that might be equivalent to being 500 meters from a police station and 1,000 meters of a fire station. And so distance in that context, even though it's a standardized unit, may not be the best way to represent the accessibility of each of these different factors and criteria. So we may reclassify them. So once we have distance, we can reclassify them to a common scale based on our understanding of how distance affects quality of life for each of the individual factors. And again, we have to standardize here. So we would start with a scale, for example, from 1 to 10, where 1 has to be the same meaning across all of these factors with regard to its propensity to produce suitability for quality of life. And like I said, it could be 500 meters from school. That can be equivalent to 1,000 meters from fire stations, or 5 kilometers from an airport. And then 2 could be different again. So we think about all those things in our reclassification step. Obviously, you don't see those thought processes going on within a cartographic model, but it happens. Finally, we decide what type of decision rule we're going to use to put all of these together. And we decide to use plus. So a simple addition, so a direct linear combination. A direct linear combination, again, is without weighting to the factors. That can be a first approximation. Then you may do other research with people and stakeholders to decide maybe we would want to weight some things more than others. For example, for certain age groups, let's say 24 to 31, schools might be more important than police stations because they're thinking of having a family. At the end of it all, however we do it, we end up with a quality of life index, which is just a type of suitability map. Before undertaking analysis, if you follow along with what we're doing in the slides here, make sure to reset your environments to match the boundary layer. That is found in the Module 5 data that we are using in this in-class examples, or for these in-class examples. That can include the workspace, output coordinate system, processing extent, cell size, set that to 200 meters, because boundary is not a raster layer, so we'll set a manual cell size to start, and the mask also to boundary. So initially we can't set cell size to boundary because it's not a raster layer. Once we have our first raster layer, we're going to revisit these and reset them all to the raster layer that we get out of the first process. In terms of rescaling, so standardizing that step for factors, we can use what's called a large function when it's important to be far from something. So when it's important to be far from a particular object or set of objects in space, and being far is better for quality of life, we use a large function. A large function is given by this equation here, which is the weighting equation, W. It's equal to C, which is a constant, divided by 1 plus the distance value to the negative power of S over M. So here we have 1, 2, 3 parameters. The first one, C, is a constant. C determines the upper limit of the rescaling value. So for example, if we wanted to have everything rescaled between 0 and 3, well, we would put 3 as C. If we want between 0 and 10, here, C equals 10. So if you want to rescale each of our particular factors for the quality of life to a scale of 0 to 10 that is standardized, then we put C equals 10. M is called the midpoint, and that's illustrated on this large function here, which is a sigmoid function. M is where you have 50%, or halfway between 0 and 10, as a rescaled value for suitability regarding quality of life for the environmental or other variable we're using here. Here we'll be using all distance variables. And that depends, of course, on what particular thing we're looking at being far away from as being good. So airports, for example, generally the further away you are from the airport, the better it is for the quality of life, because you're unlikely to be disturbed by airplanes, jets, and the noises that they bring with them and stuff like that. So in this case here, for the midpoint, we chose 5,000 meters. And so by the time you're 5,000 meters away, you have half of the total amount of suitability, which is 10, in terms of quality of life. And as you increase the distance here up to right about 9,000 or so, then you're almost at 10, which is as good as it gets for not having noise pollution because of an airport. And everything after that value in terms of distance, so going this way, is pretty much the same thing. It's all optimal in terms of the quality of life for the distance from airports. And in ArcGIS, in Python, this then says that it's better for distance from airports to be around 9,000 meters away, 10 kilometers away. You'll have the best quality of life. Anything closer, and you start to decrease the quality of life because of air pollution, and anything between 0, for example, and just over 2 kilometers, 2,000 meters, maybe about 3,000 meters here, you have a very low quality of life with respect to noise pollution from airports. In Python, what we have to do then is we take our airports right here that we have, and we create a distance surface from that, which you can see illustrated with the green to red. Green is closer, yellow is further, and red is the furthest from the airports. And we use the Euclidean function to do that. We can also do the same thing for hydro lines. The same function for hydro lines with the same midpoint. So we get the Euclidean distance from hydro lines as well. So we have a raster variable for hydro lines and airports, here and here. Then we set our parameters, C, S, and M. And we put 10 point, that's our C, the constant that determines the maximum value of suitability on this rescaled standard, 5 for the spread, and 5,000 meters for the midpoint. So M, it's important here to note, is always in the units of the environmental variable. And then we simply apply this equation here to each distance surface. So in this case, airports D, which is the Euclidean distance surface here that you see, that is put right here in the equation. The result of this is the airport's factor for quality of life, and likewise for the hydro lines. So that's called a large function. And here we did it using an equation. You could also use the Rescale by Function tool in ArcGIS Pro. It has the ability to rescale by a number of different functional forms, such as the one we just saw, which is called large. So large is the one I just showed you. Whereas we used an equation, we could do it here without the equation using a built-in tool, which saves us time having to type in an equation or figure it out. In this case, if we did it through the tool, we'd say input raster would be the distance, the name of the output raster, the factor, for example, airport's distance, airf for air factor, the type of function large, and in the help file you can see all the different types of functions that are available. And then the midpoint, the spread, and the from and to scale. In this case here, 1 to 10 instead of 0 to 10. And as long as it's the same for all of the variables, it's fine. It could be just 0 to 1, just like a fuzzy membership if you wanted to. The magnitude here does not matter. It only matters if you're changing things within a given range of magnitude to different magnitudes. But if everything is going to be the same, 1 to 10, 1 to 100, 1 to 5, 1 to 3, it doesn't matter. You will have the same results. In Python, we could also use that tool. First, we have to create the type of function we want. And in this case, for large, it would be called TF large. And we give the midpoint and the spread. The spread, by the way, just determines how fast or steep that sigmoid goes. So the smaller the spread, the more steep it is, the more vertical. The larger the spread, the more gradual it will be. And generally, you want some sort of reason to choose a particular spread value. Here, we're just using one that seems reasonable, but it's not that's not a justifiable reason to use it, for example. So we create the TF large variable, and that's just like a neighborhood variable that we had to create. And then we use that in the rescale by function. So we then call rescale by function, give the name of the input, distant surface. The name of our TF large goes next, which is just called large. And then the range we want to rescale by, 0 to 10. And I apologize here, that's a little different than the 1 to 10 right there. So I should have been consistent on both of these, but as long as we do all of them the same way, as I said, it doesn't matter. And then we do the same thing for the hydro lines. And we just reuse that large variable, which is a reference to a TF large function with 5,000 meters for the midpoint and 5 for the spread. We can also have a small function when it's good to be close to things. So here, between 0, let's say, and about almost 3,000 or so, you're at a maximum suitability for quality of life, right up here. So if you're within 0 to about 3,000 meters, you have the best quality of life with respect to distance from a particular type of amenity in space. And it's the same equation. The only difference is the exponent is positive instead of negative. If it's negative, it's a large, and it would go like that. If it's positive, it's a small function, like we see here. And we could use schools, fire stations, paths, police stations in the exact same way. We get distance surfaces for each, and we apply the equation for each in Python as a map algebra statement, or a set of map algebra statements. And that will then produce something rescaled from, in this case, 0 to 10 for every single one of the different factors, to create a schools factor, a fire factor, a pass factor, and a police factor. Likewise, we could do that through the rescale by function using a TF small. Now, some things or some types of functions you may conceive of requiring are not provided within the rescale by function tool in ArcGIS Pro. For example, major roads. It's good to be close to a major road, but not too close. It's also good to be not too far from a major road. And we therefore conceive of a function that looks like this. And we have here a midpoint of 1,500 meters. So it's optimal to be within 1.5 kilometers of a major road. That's where we have full suitability with respect to the quality of life and distance from major roads. It's not very good to be too close, so up to about 500 meters here. You have a lot of noise pollution as well as air pollution from major roads. And as we start to get from around 500 meters to 1500 meters, we start to have an increase as we get towards that optimal distance. Then, after 1500 meters, we start to get further away from roads, and they become inaccessible. And so we have a decrease in the suitability with respect to the quality of life. And so this function here looks like that. Again, we have C, the constant, which tells us the maximum value to rescale to. And then we have Euler's number, E, to the power of the negative natural logarithm of D minus the natural logarithm of the midpoint squared, divided by 2 times the spread squared. So it's a little more complicated of an equation, but it gives an example of one that you cannot do without map algebra. So for major routes, we get our Euclidean distance, and then we set the parameters C, M, and S, just like before. 10, in this case, 0.5 for the spread. And then we have to use the natural logarithm, which is in the math library of Python, math.log of 1500. Once we have that, we apply the equation by substituting for D, the distance right here, our major routes. And then we have a routes factor coming out the other end that describes that it's good to be somewhat close, but not too close or too far from a major road. So in all, here we have 7 factors. And to use an equal weighting, we'll use a weighted linear average so that our output range can range between 0 to 10. It doesn't mean there will be a 0 and a 10, but it can range that much. And since we have 7 factors, the weight of each is 1/7. So it's simply 1/7 times the sum of the weights, or 1/7 times the sum of the cells in the individual layers. So the sum of the factors, I should say, not the weights, right here, where X is just one of the raster layers or factors that we produced. And here it is in Python. It's pretty straightforward. We just add them all together on one single statement. And again, that would require 1, 2, 3, 4, 5, 6 pluses within a model. So it would be a little complicated to do that set of pluses. And we divide it all by 7. And we have then here the result, which is a quality of life layer based all on distance from different amenities. So in this case, red areas are the best areas to be, and blue areas are the worst for the quality of life, based on these factors, of course. And this is a set of assumptions that we're making. You could conceive of more things that could be added into such a conception of quality of life than we've used here. But the general idea still holds. To create the quality of life index, I'm going to start by bringing in, as you've seen here, schools, police stations, fire stations, paths and trails, major routes, hydro lines, airports, and boundary. Then, the first thing I do is set my global or application level environments. I'll set them to match boundary, as many as possible. So output coordinate system, boundary, extent, boundary, I set a cell size of 200 units and mask as boundary. And I'll change that to preserve resolution for the cell size projection method, although we won't be using it in this context. We'll put it there just in case. We can't set the snap raster yet because we have no raster, but once we create our first raster, we will then reset all these environment settings to match the first raster we create. So then I'll open up the Python window. And since this is the first Python session, since I've opened ArcGIS Pro, I'll start with my imports. I'll say from arcpy.arcpy.sa import all. And then I'll import my environments. I'll say from arcpy import env. Then I'll just check an environment setting. I'll check, let's say, the output coordinate system. I'll say env.output coordinate system .name, City of Ottawa. That's just the name of this output coordinate system. It's a modified transverse Mercator zone 9, which I just called City of Ottawa when I created it. I'll check the extent to make sure it's an extent object. And it is, so that's good. And I'll check, I should say, not set, but I'll check the env dot mask. And that's set to boundary. So this is, again, just to check that all of our global environment settings have been passed down to the Python window. So that's good. So the next thing I'm going to do is start computing my first Euclidean distance surface. I need to compute one for all of these things. So I'll start with the first one in the table of contents, schools. I'll call it SCHOOLD for distance equals Euc distance. And then I'll choose schools. I'll just drag it, click on it here, drag it, and drop it in here, like so. And hit enter. And that will create my first Euclidean distance surface from all of the schools. I will use that then to reset all my environment settings. So I'll just close my Python window for a second, and I'll bring this just above boundary. And there it is. It's within the boundary, so that's great. That's what we want to see. The boundary is used to mask out the entire raster. So again, that's a square or rectangular raster, and it's all no data cells where we see blank. So I'll go to my environments now and reset everything to match schools or school D. I'll put coordinate system, school D. Extent, school D. Snap raster, school D. Cell size, school D. Mask, school D. And I'll click OK. Now I'll go back to my Python window and I'm just going to check to see if it's got them. So I'll just check the mask. Now it's school D. The output coordinate system still the same, etc. So those have been passed down. I'll check the cell size. And it's referencing the Euclidean distance SCO1, which is what it called it when I created it, and called it school D in the table of contents here. So now we'll create the other Euclidean distance surfaces. So I'll say the next one is police stations. I'll say police D equals Euc distance, and I'll choose police stations. There we go. Enter. Then fire. So I'll say fire D for distance equals Euc distance, and I'll choose fire. Next, paths and trails. I'll just call it path. Paths D equals Euc distance, and find paths and trails there, and here we go. Next, major routes. I'll just call it routes D equals Euc distance and major routes. Hydro lines, hydro D equals Euc distance, hydro lines. And then our last one, airports, I'll just call it air D equals Euc distance and airports. So now I'll just close my Python window to check things out, make sure they all make sense. I'll start by turning everything off. And I just hit my control button on the keyboard and I just click on the first item in the contents pane. And that will automatically turn them all off. If I want to turn them all on, same thing, control and click, control, click. So we'll start with the airports. There's our air distance, and that's the airports. Makes sense. Looks good. Hydro lines also make sense. The next one, I'm just going to collapse these sequentially as I go up here. Paths D and paths and trails. Yeah, that looks like it makes sense as well. Collapse that one. Fire and fire. Good. Police and police, turn off the fire. That looks good. And finally, the last one will be schools to check. I'll have to turn off the police there and the police here and turn on schools. And that makes sense. So why do we do that? That's again, a ad hoc validation. When we're creating many distant surfaces like this or any operation that we're repeating many times in Python, it's always good to make sure that each of those times it works as expected, because it's very easy to accidentally reuse the same variable name with the wrong data when you're doing stuff like this. So it's fundamental that you're sure that everything that went in came out as you wanted it to. So now I'm going to remove all the vector layers since I don't need them anymore for my quality of life stuff. I just needed to get distances from those. So I'll remove those. And I'll also remove boundaries since I don't need that anymore either. So we have those distance surface all here. So the next thing is I'll go back to my Python window and we're going to use the equation, which is C, our constant, divided by 1 plus the distance divided by the midpoint to the power of the negative value of spread for hydro lines and airports. So things that it's good to be far from, we'll start with. We should give our values to our parameters. So C, comma, S, comma, M, and those will be equal to 10, 5 as the spread, and a midpoint of 5,000 or 5 kilometers. So we want our output range to go from 0 to 10, our spread to be 5, and our midpoint to be 5,000 kilometers. So once you're more than 5,000 meters away, you have greater than 50% in terms of the contribution or suitability for quality of life with respect to airports and hydro lines. So then I'll say air, F, for the air factor. And this will be equal to C divided by parentheses. And then inside those parentheses, I'm going to have my expression, which is 1 plus parentheses. Since we're going to have a division in here, we'll have the parentheses. And this will be air D divided by M. And then 2 asterisks means to the power of, and then negative S. So that negative spread value. And then we'll hit enter. And then we'll have a look to see if our air factor makes any sense. So, because it's good to be far from airports, if I click close to an airport, I should have values near 0. So that's near an airport, identifying. And we have a value of 0.000324, very close to the airport. Then I'm just going to hit my up arrow and change air F to hydro F. And it's the same equation, except we put hydro D here. Because again, it's good to be far from hydro lines. And if I look at it, oh, it looks like it makes sense. Again, low values near the hydro lines. And we get a value of 0, near 0, obviously. Very close to 0. Right on a hydro line, it would be 0. So we now have our airport factor and our hydro factor. Next, we want to look at things that it's good to be close to. And it's going to be the same equation again, except with a positive value of spread. So we remove the negative. So it's easy here. I'll just hit my up arrow, and I'll start with police stations. So I'll call that police F. And here would be police D. From right up here. And then I remove the negative sign from S, and I hit enter. And there it is here. The white values again are high, near 10, and the low values are near 0. In the very white areas, in the centers of those particularly, right by the police station, you'll have a high value of suitability for the quality of life, or so almost 10 there. Then I'll hit the up arrow again, change police for fire. Like so. So paths and trails, good to be close to. And again, just having a quick look at it. Yeah, that looks good. So we now have our air factor, hydro factor, police, fire, paths, schools is the next one that is good to be close to. And we just called it school. We'll call it school F output, and the input here, school D. And we're all done, and that looks good too. All the schools, very bright values around them. Next, we want to look at, or the more challenging one here, which is going to be the routes. So if you recall, it's good to be somewhat close to a major route, but not too close and not too far. And so we have to use the exponential equation. I'll say CSM this time equals 10. Just put the point there so it's a floating point value. 0.5. That's the spread or standard, or kind of like a standard deviation of this function. And then the distance that is optimal as a logarithm. So math.log, and we said 1,500 meters, so 1.5 kilometers would be the best distance to be away from a major route. So we have that. Finally, then we can say routes F, and that's equal to C times math.exp like so. And then the negative value of parentheses, and then inside them we have the natural logarithm math.log major routes. So that's routes D. And then just outside of that, minus M, the midpoint. Or I shouldn't say M here is the spread, these kind of how wide that function is. That means how fast it rises to 1,500 and how fast it decreases after 1,500. And then outside of those parentheses, that'll be squared, divided by parentheses 2 times parentheses, s squared, like so. And then we'll hit enter. Okay, so we can't use the math functions here on rasters directly. We have to use raster-based functions. So exp, which is a function in Spatial Analyst, math tools. And then here, that would be the ln, or logarithm. Let's see if that fixes that. exp, like that. There we go. And then we'll hit enter. It says ln is not defined. It's because I spelt it wrong, I think. Yes, L small n, like so, to be consistent with exp. So those are the raster toolbox functions. And here we go. Now we can run that, and it's done. And this one should look weird. There it is, yes, and it makes sense. So now that we have all of our factors, we can add them together within a weighted linear combination, where the weight for each layer will use equal weighting. They'll all be equal to each other, I should say. We'll have equal weights. And since we have 1, 2, 3, 4, 5, 6, 7 different layers going into this quality of life index, which I'll just call QOL, I'll just say 1 divided by 7 times parentheses, and in the parentheses, I'll add up my individual layers. So that's 1/7 times each layer. And that just ensures, again, that my output range will be between 0 and 10. So I'll start with air F plus hydro F plus police F plus fire F plus paths F plus school F plus routes F. And so we have our 7 there, and we just have to hit enter. And that adds them all together. And now I can close my Python window, go back to the zoom out to quality of life. I think I'll turn all the layers off and just turn on quality of life like that. There we go. So that's the final quality of life layer, and it ranges between 1.42 and 8.9. So we don't get anywhere that's a perfect 10. But we can see these light areas, especially around here. In many of these very light areas, we have the best quality of life according to the parameters that we used, or the factors that we used. I can look at that in a different way. So go over to my Appearance tab, Symbology, and I can classify that if I want. Just a stretch with a different or more multicolored scheme, such as a shaded relief scheme like that, if you wanted to. So in this case, the very high values are white, then dark red to kind of orange, yellow, green, darker green, then to the kind of very light green, or white to then to green. Not white, but yellow to green. So here we can just kind of see things a little bit differently. So that's the quality of life final map.